Hello, my name is Jeppe Byskov and I'm the Director of the Additive Manufacturing Center at DTI. In these videos, we're going to have a closer look at the selective laser sintering technology, also known as SLS. If we take a look at the technology chart here with the 7 different basic technologies, we are in the category of powder bed fusion. We are looking at polymers today with the technology called SLS, selective laser sintering. Let's have a deeper look on the technology. So if we follow the red arrow here, we can see from this ISO standard that we are dealing with a polymer technology. The state of fusion is thermal reaction bonding, that is, we have some heat source to glue the particles together. The material feedstock is powder, and the way we actually distribute this material in the printer is by the technology called powder bed. The basic AM principle is that we have selective fusion of the material in the powder bed so that everything that gets hit by the heat source is becoming the part, and all the powder not being hit by the heat source is just still powder. And the basic process category is what we call powder bed fusion. Let's take a look at what powder bed fusion is by looking at some of the machines and how the technology actually works. Let's have a closer look at a machine based on selective laser sintering, or SLS. As you can see, some of the main components is of course the build chamber, the chamber in which you print your parts. Then also the laser, which is the actual heat source that you use to sinter together the particles. You can see the laser in the top left here, shooting the laser beam onto a mirror, controlling where in the print bed you actually do the heating. You have a recoater system. It can work in a few different ways, but basically you have an amount of powder that is then recoated over the print surface, so you can do this printing in the powder bed. You have heating lamps, which are also very important, because with SLS you heat the entire powder bed up to just below the sintering temperature, and then you give it the final small kick with the laser. Some of the most typical print parameters for selective laser sintering would be printing in PA12, one of the most common materials in SLS, printing about 0.1 millimeters in layer thickness, and heating the entire chamber to about 180 degrees, just below the melting temperature, and then with maybe a 40 to 50 watt laser sintering together these particles. Taking a look at the process flow for SLS, there's much more than just the printing in it. First of all, you have to heat up the build chamber to just below the sintering temperature. Then you have the printing. Between each layer you do this recoating. As mentioned, typically 0.1 millimeter layer thickness. When you've deposited a layer, sintered it together, you lower the build platform and then deposit another layer. Heat it up again, sinter it. When the part is finished, you need to cool down the build chamber in order to avoid deformations. But you can do that in the build chamber outside the machine so that you can actually utilize the machine capacity to start the next job very fast. Final step is of course unpacking the parts. When the entire build job has cooled down, you manually break out the parts from the big build platform powder cake. We have seen a sketch of how these printers work. This is what it looks like in the real world. We've taken 2 examples. One is a desktop model on the left. On the right we have a more industrial model. There's a number of differences between these machines. For instance, how big they are, how big parts they can build, how fast they are, and obviously the industrial machines are faster. But of course also the price of these 2 are very different. To show you how the printers actually work and what the workflow related to the process is, we have a small video here. The first thing you could see was the files being prepared on the computer. These files are then sent to the printer, and what we see here is a layer of this plastic powder being deposited, and what we currently see is the laser scanning the parts, so you actually melt together all of the powder going into the physical parts here being printed, layer by layer, until you have the full build job completed. When the job is completed, you take it out of the printer, and typically with a station like this, you have a cleaning station, you can take the full build platform, put it into a machine like this. You apply the right working conditions, like you have gloves and you have a mask. Then you break out the cake, as we call it. You have all of the parts here with a lot of powder on it. You do a rough manual cleaning of it. All of the powder you can reuse, so you just mix that into new powder for the machines. The next process here is blowing on the parts, and here we actually use the powder used for printing to keep the parts nice and clean. You very often do some air blasting, and in this case also, since you have some internal channels, you do cleaning with a piano wire. Then you have the final parts, and they are ready to be actually used. Let's move on and look at the pros and cons of the SLS technology, and we're going to have a few examples of what it's good for and not so good for. Looking a bit more into detail on the pros and cons of the selective laser sintering technology, we can take a look at this sketch. We see over to the left, SLS is not represented when we need something visually nice. This is because SLS is better suitable for functional parts. Functional parts where you either require some strength or some good elastic properties, generally good mechanical properties. We can see we have some rather good tolerances and generally good material properties. Furthermore, we can see we can have it chemically resistant, flame resistant, and biocompatible. So we see it often used in, for instance, the food industry. One of the very big advantages with selective laser sintering is that you do not need any support. This gives you a lot of design freedom, even more than you have with many of the other 3D printing technologies. Furthermore, you can sort of just nest it three-dimensionally into the build chamber. Because you don't have this support, you just fill up the whole build volume, making it very good for serial production of parts. When you don't need support structures, you have an even greater design freedom, so you can make internal channels completely freely without thinking about any of the support. However, you should keep in mind that you should always design the parts so that you can remove the powder from the parts in the cleaning process. So for instance, when you build these channels and cavities, it's very important that you can actually remove the powder. Finally, you get a very uniform surface finish, since you don't need the support and you don't have these support remnants on the parts. Another advantage of the SLS technology is that we have really good isotropic material properties. That is, however we orient the part in X, Y, or Z direction, we get pretty much the same characteristics. All you need to be aware of, as you can see in the bottom of the table, is that you have a difference in the elongation at break, depending on if you build it in the XY plane or in the Z plane, which is the build direction. If we take a look at the picture to the left, we have printed some tensile bars. This is the way we typically use to quantify the material properties, printing these bars, testing it, and document that we have good and uniform properties. When we do this on a daily basis, we always place the test pieces in the corner of the chamber. We do that because potentially this is where we have the lowest temperature, which can lead to the weakest points. So by putting the tensile bars there, we make sure we have a worst case scenario. When we do this printing of tensile bars, on each build job, we always make sure we have a good quality and we can always document what the properties are. One of the other great advantages with the SLS technology is that once you've removed the powder from the part coming out of the printer, you have a ready-to-use part in your hands. There's then the possibility of doing some more finishing depending on the properties you want from the part, but typically you would use the part directly from the printer. As an example, we have this handle. You use that for cleaning conveyor belts in slaughterhouses, and you can use it directly from the machine. One of the things that is both an advantage and a disadvantage of the SLS technology is that it is very much minded on the industry and on industrial use. As mentioned, you can have this in desktop models. We saw this earlier, but still then it costs around 11,000 euros, which is well above the budget for a normal hobby printer like you would see with the FDM technology. You would have much lower prices. And 11,000 euros would typically be more than you would spend as a private person. So this is one of the reasons it's very much minded towards the industry in one way or the other. If we go a level up to the more industrial printers, as you see on the right, it is an EOS printer costing about 250,000 euros. So then we're up at a price range where it's good for as a production equipment, but you need also to print quite a lot of components to justify that kind of price. One of the main drawbacks of the SLS technology is that it has quite a high surface roughness directly from the machines. Typical RA values is between 5 and 10 micrometers, depending on how you have oriented the parts, as well as the layer thickness and some of the other build parameters. But directly from the machines, relatively high roughness. There are a number of ways you can post-process the parts to get acceptable surface roughness. Depending on your requirements and your applications, for instance, we see in the food industry quite high requirements, but there are equipment that can bring you to that level of satisfaction. One of the things that is both an advantage and a disadvantage with the SLS technology is that it's super good at printing small to medium number of parts. But if you have to just have a single prototype, then it's relatively slow compared to some of the other technologies. We can find the reason for this in the flow chart that you see here. Typically it takes about 2 hours to warm up the chamber to about 180 degrees. The entire print process with all of the layers to be built typically takes about 48 hours, where each layer takes about 10 to 30 seconds. Once it's been running, it's got to cool down, and the cooling time is typically about half the time it took to print. So in this case, it must be cooled down for about 24 hours before you can start to break out the parts. Breaking out the parts, depending on how many and how complex, takes about 1 to 2 hours, but it completely depends on the number of parts and the geometry. So summing up, looking into the pros and cons of the SLS technology, we can see on the advantage side, we have that SLS requires no support, giving you a greater freedom. It's excellent for production of small to medium-sized batches. And it has some very nice mechanical properties. On the disadvantage side, it has a relatively high surface roughness. And compared to some of the other technologies, it has a relatively long lead time on prototypes. Now, we're going to take a look at some of the design possibilities that the SLS technology provides us with. So, taking again as an example this handle that we saw before, you can see some of the advantages here is you can have a rather complex internal structure. We have one channel in which you have steam, another channel in which you have vacuum. This is pretty much the only way that you can manufacture this, really bringing into play the advantages of 3D printing. However, there are a few design rules that you need to pay attention to here. For instance, for the small steam channel, you need to have a diameter of at least 5 millimeters in order to be able to clean it from the powder after the printing is done. These are rule of thumbs, so it really depends on, for instance, the length and the design of your actual part. One of the other design options that you have with 3D printing is that you can print lattice structures. This, of course, also applies to SLS technology, where it's particularly good because you don't need any support, as we discussed before. As an example, we have this bike helmet here, where you can see it's made up of these honeycomb structures. It has very good shock absorbing properties, so it's much better than a regular foam bike helmet. Another great example of using 3D printing is using it to make lightweight constructions. In this case, also with SLS technology, we have an example of a robot gripper. The weight of the part could be reduced from 1300 grams down to 625 grams. This saves you a whole lot of weight, which allows your robot to run faster, and you might even be able to change the size of the robot. One of the other benefits of 3D printing is that you can apply what is called part consolidation. That is, we can put parts together, reducing the actual number of parts. So, for instance, instead of having 72 parts, as the conventional gripper here was made of, the 3D printed version has only 8 different parts. This saves you a lot of time and money in the assembly phase. Summing up these different examples, you can see some of the general design possibilities that we get, and we can see in all of the cases is the design freedom, the lightweighting of the parts, and optimizing some of the properties of the part. Next topic, we're going to have a look at the guidelines for how we design for the SLS technology. Here we take a look at some of the guidelines and the design rules for 3D printing. We borrowed this very nice sketch from 3D Hubs, and we've highlighted some of the features that in our experience most often gives you complications when designing for SLS technology. Taking a look at the first design feature here, we're talking about embossed and engraved details. This can, for instance, be used to mark your parts. In this case, we have a robot gripper. It's been marked with an R because it's the right side of it, making it easier to mount for the operator. There's some features on the right side of the parts to guide the operator in how to mount it also. On the limitation side, on the design side, you get the best results if each of these features is at least 1 millimeter in the height and depth and 1 millimeter in the width. Looking at the next design feature, we're having a look at escape holes and channels. Typically, you recommend a minimum hole size of about 5 millimeters. But it very much depends on the geometry. So if we take the part labeled with number 1, you would see this is going to be very difficult to clean. Typically you use compressed air or you use piano wire. And if you do that with these very sharp angles, it's going to be very difficult to empty it for powder. Going in to the second and the third option, you see it's much easier both to get the piano wire through it and to use compressed air to actually blow the powder out of it. The last option that we have included, labeled with number 4, is actually printing a solid wire up through it, and you can pull it out afterwards. One of the possibilities we get with the SLS technology is that we can actually make moving parts. But you have to be very aware of this in the design phase because you need to make a clearance of at least 0.3 millimeters so that when you clean the part from the powder, you have this moving clearance. This means that we can actually print some parts and some assemblies where we have movement built into it. We can take a look at the robot gripper where we build a spring into it which allows it to move, and when the part is printed in a single piece, it can still move when it comes out of the printer. This is a great advantage of the 3D printing, but it also really challenged the engineer to think out of the box. Taking a look at the tolerances, which is always very important when talking about 3D printing, we can see we typically have a standard tolerance of about plus minus 0.3%, but there are some features that you need to keep very much in mind because you can have large deformations. If, for instance, you build large flat surfaces, if you're trying to build very thin walls or very thick walls for that matter, if you have large changes in cross-section area, as you can see in the sketch to the right, you tend to get this wobbling, you get a big deformation. Finally, the orientation of the part. Even though we have a relatively isotropic process, the orientation of the part can still have an influence on the tolerances. The design rules that we already have mentioned are of course only guidelines to give you the basis for the best possible results. Of course there is an opportunity to push the boundaries, but if you would like the design to be the same when it comes out of the printer every single time, then it's generally a good idea to follow these guidelines. The next topic is which materials can we use to print with the SLS technology. Taking a look at the available materials for SLS technology, we have this very nice pyramid that gives you an overview. The materials marked with green are commercially available. The yellow ones are used for R&D, typically at universities and documented in papers. The red ones are not available for SLS. It's divided into commodity polymers, which are typically relatively inexpensive, engineering polymers, medium expensive, and high performance polymers that are often quite expensive. By far the most used SLS material for many years has been PA12, but we see a very increasing interest in PA11 since it's a more green material. The most used material for SLS is PA11 and PA12. They have rather similar properties, but the main difference is that the PA11 is a sustainable bio-based material, whereas the PA12 is based on oil. They have slightly different properties, but both PA based and therefore quite similar in mechanical properties. Having a closer look at the mechanical properties of PA11 versus PA12, we can see they have very close to identical properties. However, we have a somewhat lower strain at break for the PA12, but besides that, quite comparable properties. As with all materials, there are some cons related to the material. Here are some of the general cons you have with nylon. First of all, UV lights turn it yellow over time, so you can see if you have older SLS parts, they turn kind of yellowish. The nylon absorbs water, and you will have this water absorption affecting the tolerances. It's relatively expensive, and furthermore, it gets quite easily static electric, which also means that it attracts dust quite easily. Besides the PA11 and PA12, you have a long range of commercially available nylons with some kind of additive. That can, for instance, be mixing it with aluminium to make alamide, mixing it with some kinds of metals to make it metal detectable and X-ray detectable. You can mix it with glass fibers, carbon fibers to make it stronger, stiffer, some of these properties. And you can have flame retardant nylon. Now we're going to have a look at what I can print with SLS technology and looking at a few different cases. We'll start out with a small case from the company Dunello, which makes strap reels to roll up lashing straps. They needed a little extra feature on their machine, and we printed a simple part for them. It's printed in PA12, then it's dyed in a black color, and that's printed something about 100 to 200 a year. Just to give you an idea of what it's being used for, we're going to watch a short video here. The machine is used to roll up the lashing straps, for instance for truck drivers. Once they rolled up the straps, we'll add a cool feature. So instead of putting the machine on the table, you can hang it in your pocket or somewhere else if you don't have a table to place it on. So if we take this part and look at the life cycle of it, then 3D printing offers some possibilities compared to conventional manufacturing. Start looking at the design freedom. It's not the most used properties for this part. It could be made with, for instance, injection molding. But in the development process, it has been really fast. We've been able to make a lot of iterations to quickly make the part fit. No injection molding tools also means that you have very low startup costs. The fact that it's only manufactured in a relatively low volume of parts means that price-wise it is competitive to 3D print it compared to investing in a rather expensive injection mold. Here we'll look at a salmon gripper to pack whole salmon sides for the company Marel. As we can see here, it's a robot gripper consisting of 8 3D printed parts. One of the requirements from Marel was that the print material needed to be approved for food contact, and it had to be metal detectable. So if something were to fall off, you would be able to find it with a metal detector so it didn't end up in the food. What we see here is the robot gripper in use, where it packs the whole salmon sides. If we take a look at the robot gripper here and we see 3D printing compared with conventional manufacturing, we definitely get some advantages. First of all, we get the design of freedom, which really gives you something extra here. You can quickly make some design iterations, quickly get it out on the market and get some feedback. We don't need any tools to make it either, so we're not going to mill out a lot of plastics. Due to the fact that we have 8 parts here, we also save a lot of money by printing it instead of having to mount it in a CNC cutter and process it out. Another one of the advantages is that we can quickly make spare parts, so if there's a risk of something being broke, you can quickly repair it with 3D printing. Furthermore, we save a lot of time with the daily cleaning because there's not very many joints, so this part consolidation really has some benefits here. Cleaning time is minimal, and pretty much the only drawback is that we have it printed in this metal detectable plastics. That means that we have both metal and plastics put together, and in this way it's difficult to separate and very difficult to recycle. The final case we see here is a nozzle used for putting icing on cookies. It's produced for the Bühler Group, again made in PA12 and food contact approved. To make it extra food friendly, it has become vapor smooth to seal the surface and so that it doesn't absorb any liquid, and it makes it really easy to clean. If we take a closer look at the model, we can see we have yellow glaze coming into the top, red icing coming into the side, and green icing coming into the opening at the side. Taking a more detailed look into this part makes it a bit more clear what it's actually doing. We can see it's making Christmas trees in different colors, and it places the icing instead of doing it manually, as we can see in the photo. This is for a real industrial production line. The different colors are spread through these different channels. For instance, we get the yellow down the top of the star, which also spreads to the Christmas tree balls. So it's a really good example of 3D printed design freedom and the possibility of making channels that are utilized for industrial use to make cookies. If we take the nozzle here and compare 3D printing with conventional manufacturing, then we can again see that the design of freedom is really important. It's a huge advantage that we can make all of these channels with very complex, challenging geometries that would not have been possible conventionally. Pretty much the only drawback for the Bülow Group was that we had designed it for printing, and it was not initially good for production in stainless steel, which is pretty much the only material that the food industry really want to use traditionally. Another advantage is that we can shorten the development time quite a lot and create some quick iterations. One of the points where we save a lot of time and a lot of tools is if we were to redesign this in stainless steel, or if you had to weld it together, something that could resemble this Christmas tree. It could take a lot of time and a lot of tools. It also meant spending a lot of time producing it conventionally, where 3D printing becomes more profitable compared to that. In terms of price, the nozzle is much cheaper to print than it is to make it conventionally. If we look at the use of the part, then there is the possibility to print spare parts. If we made it conventionally, this would be a very advanced item that requires a lot of craftsmanship and a lot of knowledge to shape it, for instance in stainless steel. With a 3D printer, we can just print the same part again if there is a need to have a spare part. And again, it's harder with plastics to recycle it, for example, than it would be for stainless steel. That brings us to the end of this first video about selective laser sintering. Stay tuned for episode 2. So first on the agenda for today, we'll take a look at the safety aspects of the SLS process. Here we see what kind of safety equipment we should wear when working with the SLS process and the powder involved with that. Since we have a particle size of the SLS powder typically below 100 microns, we need to be careful not to get it into our lungs, so we need to use some respiratory filter when handling the powder. This can either be a full face mask, as we see on the left, with a filter and safety goggles built into it, or it can be a filter like the one we see on the right. The most important thing is that it uses a P3 classified filter. In addition to this, we must also wear rubber gloves when we handle the powder, and workwear clothes and a pair of safety glasses. Finally, also safety shoes when we move around in the production and work with the powder. When working with the SLS process, we should be aware that the powder itself is not approved for instance, food contact. However, the finished part can be used in contact with food, for instance, containers for liquids or for medical equipment. Also, the powder is very static and, as mentioned, in some very small particle sizes, and this means that it can lead to an explosion. To reduce the risk of explosions, we need to make sure that we only use a very small amount of powder at a time, and we always clean up after ourselves so we don't have any loose powder lying on the floor after we've been mixing the powder. So the floor must always be vacuumed right after the process to keep it clean and reduce the risk of explosion. The fact that we work with powder that is explosive means that we need to have a workplace assessment that is in accordance with the ATEX directive. This also means that we need a new ATEX workplace assessment every time we make some changes in our production or to the procedures that we use in the production. Or as a minimum, we need a new assessment every 3 years. The ATEX workplace assessment is there to reduce the risk of a powder-related explosion in the production. In the previous video, we looked at the actual printing process, and here we'll take a look at what comes before and what comes
after the 3D printing process itself. First, we'll look at how we prepare jobs for the SLS process, where we take advantage of the fact that we can stack the parts in 3 dimensions. Unlike most other printing process technologies, we can actually pack the parts in 3 dimensions in the build chamber because we don't need support in this process. Here I have an example where we have 10 different parts and we need 4 of each part, so that's going to be 40 parts in total. In addition, we have some tensile bars that we use for quality control of each build. You see them in the top right corner of the white square. This is one of the ways that you can place all of the parts in the printer by doing it manually and moving it around yourself. Or we can use a function that is available in most preparation programs for an SLS printer called 3D nesting, where the computer does it automatically. So let's have a look at that. If we look at the pictures on the right, we have 2 build jobs as seen from above. In the top picture, I have defined the Z-axis on all of the parts, and in the bottom picture, I have given the computer complete freedom, and it has oriented the part so that we have the smallest cross-sectional area lower in the build chamber, and therefore they are placed more randomly. We'll see it much more clearly as we move on to the next slide. Here we look at the 2 build jobs from the side. On the left we have the predefined build job, and on the right we have the job that has been freely oriented by the computer. What separates the 2 build jobs is the build height, so how high we build in each job, and then it is the 2 graphs that are on the left of each image. On the 2 graphs we can see the cross-sectional area all the way up through the build, and the goal here is to get it as vertical as possible. So it is quite clear that on the freely oriented build to the right we have an almost vertical line where the computer has distributed the parts more evenly, whereas on the left we have a graph that varies a lot, and it actually means that in the build job to the right we get a much smoother build, and that is what we are striving for. If we look at the benefits of the predefined build, then it is that we have 4 identical parts, and in this case, if we have oriented them identically, then we will get 4 relatively identical parts out of the printer. On the other hand, if we look at the free orientation, then the parts are oriented differently, even though they are identical. This can make them slightly different in tolerances, in surface and in quality. On the other hand, with the free orientation, we have a more evenly distributed build job, where we have a more evenly distributed heat throughout the build, and the quality should in practice be better than with the predefined. So basically it depends on your needs, and you can choose one or the other nesting strategy. One of the things we can also do when preparing SLS jobs is that if we have many small parts belonging to the same order, then we can pack them in what is called a nesting box, as you see in the picture here. So we can actually print a box around our parts, and we can add a mark on the box saying which kind of parts it is. For instance, you can write the order number or the task number on the box. That way you have tracking throughout the production, and you have all the parts packed together throughout the production. This is a great advantage when you're dealing with many small parts in the printing process. One of the things we also need to be aware of when printing with the SLS technology is that after we've packed all of our parts, for instance with the 3D nesting, we need to scale them. Depending on what material you're printing in, there are different scaling factors. For instance, we can see here the scaling factor for an EOS P396 with PA 1101 and PA 2200. Often the scaling factor you enter is pre-programmed into the software, so it automatically scales your parts and considers the shrinkage that happens when you slowly cool the parts in the printer. So that is what we are doing here. We are compensating for the parts contracting when they are cooled down. Now we have looked at how we prepare our build jobs by packing the parts and scaling them before the production. The next thing that we'll look at is how we prepare the powder that we use in the printing process. With SLS PA12, we typically use a mixing ratio of 50% used powder and 50% new powder. This amount can vary, but this is typical numbers. This means that we reuse some of the powder that has not been turned into the massive parts that we produced in the last build. Consequently, we have a much lower waste and we utilize the powder much better. With some materials, it's possible to change this mixing ratio. There are some materials that require, for instance, 100% new powder, but there are also other materials where you can print with only 30% new powder and 70% used powder. So in that way, you can have an even lower amount of waste. But if we take the PA12, then the quality will drop quite a lot when we add more than about 50% used powder. Once we have mixed the powder, we can add it to the printer, where it needs to stay for a while to discharge from the static electricity before we can start the printing process. So now we have mixed the powder and added it to the printer. Now we have to ensure that the printer has been properly cleaned before we can start the printing process. This is because there might be some powder residue from the last build, and this will burn to the inside of the build chamber as we heat it up to about 180 degrees. So we need to thoroughly clean the build chamber and the process chamber that we can see in the picture on the right. Also, we need to clean the collection bins and empty them of residual powder from the last build. In addition to that, we need to clean the lens. As we can see in the table on the left, there are different intervals for when the lens needs to be cleaned, depending on what kind of powder we use. That way, we can make sure that all the energy from the laser going through the lens actually reaches the powder. The whole cleaning process for the printer after printing takes approximately 30 to 45 minutes, and then it's ready for a new print job. Now we have looked at how to prepare the printer for the printing process, and we covered the actual printing process in the previous video. So now it's time to look at how we clean the parts after a build job so that they're ready for the post-processing. We'll also look at how to sort the powder so that we can reuse this in the next build jobs. What we need to be aware of is that we have some powder from the build that we cannot use, so this is just waste. The waste is the powder that is stuck to the parts when you take it up. Also, powder that is lumped together, we cannot reuse this either. It's simply too hard baked. On the other hand, all of the powder that we have along the edges of the build chamber, as well as in the top and the bottom of the build chamber, this can be reused. And the same goes for the powder in areas where there's been plenty of space between the parts. We have all this powder inside the unpacking station, as we can see in the picture on the right. And we push the powder that can be reused into a sieve on the right side. This is 0.3, as you see in the picture. The powder is then sieved and poured into the container below so that we can reuse it and mix it with fresh powder so we can use it in future print jobs. After we have taken our parts out of the build chamber, there's still some powder stuck to the parts. Therefore, we need to put them into a blasting cabinet. First, we blast with the same powder that we used in the printing process. Afterwards, we need to get rid of the last powder. For instance, if there's been any channels in the parts, it's not enough to just blast it with its own powder. Then we also need to blast it with glass. In the end, we blast the parts clean with air to get the last powder remnants off, as well as glass remnants from the glass blasting. This can be done in a cabinet like the one you see on the right. This is a manual cabinet where you can blast all the parts, or you can do it automatically with a machine like this, where we take the large and the small parts and pour them into the machine, and then it handles the glass blasting for you. What we see in the video here is the operator taking an SLS build job, putting all of the parts into the machine, which is called a rapid cleaner. While it's running, the machine blasts the parts and removes most of the powder from them. You can quickly check the parts afterwards and blow them clean with air if necessary. But otherwise, the parts are pretty much ready for post-processing when they are done here. In this drawing, we see the powder flow through the entire production, and we see which equipment is required to have an industrial AM production with the SLS process. The powder starts by entering a multi-box. We have some used powder and some new powder, which is poured into the sieve and is mixed into a new box, which we can then load onto the 3D printer. The printer then prints. When the printing is done, we take out the build chamber. Here we can see we use a lifting trolley and we move it to the unpacking station. Here we unpack all of the parts and sort the powder that we can use and throw the rest of the powder out. The powder that can be reused is stored in the stock, so it's ready to be mixed with new powder for future print jobs. Next up, we'll have a look at some of the post-processing options that you have for 3D printed SLS parts. The list below contains some of the most common post-processes for the SLS printing process. First we have deburring, we have smoothing that seals the surface, we have dyeing, and then we have painting and hydro warping. We'll take a closer look at the first three, and you can see an example of painting over to the right. This is an SLS part that has been painted with wet coating, and in the two pictures below on the left, we can see an example of hydro warping and a small sketch of how it works. Let's start by looking at deburring. We have a machine here where we can use different media with which we can deburr different kinds of parts. It's a relatively easy accessible process where we just put the parts in with the small chips, as you can see in the picture on the right. The machine then spins the parts around, and in that way the parts are deburred. One of the disadvantages is that the chips have a certain size, which means that they cannot get into channels, we cannot get them into holes, and we cannot enter sharp cavities. If the parts are left in the deburring machine for too long, there's also a tendency for the edges to get rounded off. So if you have some external sharp edges, then they will be rounded off if you keep it in the process for too long. In the graph below, where deburring has been done, we can see how the surface roughness changes the longer we give the parts in the deburring machine. In this example, we have a raw part, and we have a part that has been deburred for about 2 hours. So it's all about finding the middle ground between obtaining the right surface roughness and not destroying the tolerances that you have on your part. Here we see how the items are placed in the deburring machine. Deburring of this type is really good for smaller parts because it has a really good abrasive effect, and because it moves the parts around so that all of the parts get uniformly deburred. On the other hand, if you have some quite fragile parts, then this type of deburring is really good. Here the parts are put in, and with vibration they are moved around more gently. This also means that the part needs more time in this second type of deburring machine. Another option for surface treatment of SLS parts is what is called vapor smoothing, which is a technology that seals the surface in a machine like the one you see in the bottom right corner. In the picture above, we can see on the left what the part looked like immediately after printing, and on the right what it looks like after vapor smoothing. The process melts the surface together, and if we take a look at the graph on the left, we can see that the black line represents a part that is untreated and has been surface roughness measured. The lower lines show that depending on which program we run, we can get a lower surface roughness. One thing to note is that the lower surface roughness we get, the more it will also affect our tolerances. This is simply because we melt more of the parts. So therefore, the more we lower the surface roughness, the worse our tolerances will also get. The great advantage of this technology is that we actually seal the surface so it doesn't absorb water. One of the disadvantages in general with the SLS technology is that the parts that you print can absorb liquids. By giving the parts this vapor smoothing process, we seal the surface so that no liquid can penetrate. So in addition to lowering the surface roughness, it really also prevents the parts from absorbing water. In this process, we need to hang all of the parts on a rack like this to have them surface treated. Depending on the size of the parts, we can fit in a different number of parts into the machine. The good thing about this process is that it also enters into the channels. So in the example here with the handle that we previously looked at, it will also enter into these internal channels. We then run a pre-programmed cycle which treats the parts to the quality that we want. When printing with the SLS process, we often print in some white or grayish material. If on the other hand you want to have parts in a different color, like blue as we see in the example here, then we can color the parts by dipping them into a liquid with some color in it. As we see on the right, there are two different ways of doing this. You can do this in a very simple way by pouring some color into a pot and then put the parts in until they have absorbed enough color liquid to be colored. What we do here is that we actually take advantage of the fact that SLS parts absorb liquids. Therefore, we can get the parts to absorb the color. It can also be done in a more industrial way, such as we see with the machine from Dimension here, which is an industrial dyeing machine to dye your parts. This gives you a more uniform surface. As we can see in the picture in the middle, we can also vapor smooth our parts after we have colored it, and thereby giving it a more glossy surface. Plus, the parts won't absorb water. An important part of 3D printing is of course the quality. So let's take a closer look at how to ensure the quality of our SLS parts. When talking about quality, it's worth noting that we're starting to see several standards for 3D printing technologies. As one of the most industrialized 3D printing processes, SLS is starting to have some standards that describe the process itself and what we can actually get out of it. As you can see in the example here, this is an ISO standard that describes SLS 3D printing with the official name powder bed fusion of plastic materials. One way to ensure the quality of SLS parts is to build tensile bars into each individual build, as you can see on the right here. So as you can see, we have placed the bars in the corner of the build plate because we know from experience this is where we typically see the lowest strength in the build job. As we can see in the picture above, we place the tensile bars on top of each other, stacked in 2 rows to cover all the layers of the full build job. Then we bring the tensile bars over for tensile testing, where we test it and enter the results. As we can see here at the red line that we have the default value from the data sheets, in this case from EOS on PA12. And in this case, we can see that all of the test results are well above. This means that we can constantly track how our build job is performing, and if, for instance, there are any layer defects, then it would appear on the graph. This is a really good tool when we run mass production with SLS. One of the advantages with SLS and printing in PA12 is that we can get it approved for food contact, because it means that we can print parts for the food industry, which for instance gives you the opportunity to make robotic grippers like the one we see on the picture here. Finally, we've made a few slides with links and references where you can find more knowledge about 3D printing in general, as well as the SLS technology. On this first slide here, we have several good links about general knowledge about 3D printing. On this slide, we have linked to some of the online magazines, and there are also some links where you can learn more about the SLS technology in particular.